Looks like it's going. All right. So we're going to start with the screen share. Where are we at? We are up to chapter 30. So let's keep the pedal down. Whoa, we don't want that yet. Whoa, not that one. All right, here we are. So this is some boring words, and here's the idea. There's an integral that calculates magnetic flux. Great. If B is uniform, we don't have to do an integral and we get this simpler result. Fine. Now, what is Faraday's law? Faraday's law is this right here. Induced voltage is equal to minus the number of turns in the loop. So if you have n loops, oh, that should be italicized, my bad, times the time rate of change of magnetic flux. So this thing right here is the derivative of this thing with respect to time. Now, what does this mean physically? That's a bunch of math. Let's go. Give me a second. If you have not practiced with the Zoom, you might want to do that for your talks tomorrow. If you haven't figured it out already, it's super annoying having to annotate. All right. So let's just start with this right now. I think you guys can probably understand this. The idea here is if you put the magnet in different spaces, the magnetic field changes. All right. Now the compass here is like the sensor that reacts to those changes, right? So, all right, great. If we want to look inside the magnet, we could see this. So notice what's happening inside the magnet versus outside. The field lines continue. So if I could just show this with a blue arrow here. Oops, let's use this blue. The field points out of north and into south. So this is the classic direction. We're going to need to know this all day today. All right, and for the next few days. So inside the magnet, we see that the field points from south to north, but outside we get these. It's a lot like thinking about the north is like a plus charge and the south is like a minus charge. Even though that's not exactly true, the math is nearly identical to that. Where it differs is inside the magnet. It's not the same as plus minus charges inside the magnet. But outside of it, you could think of it as electric fields point away from plus, magnetic fields point away from north outside the magnet. All right. So now let's say I get a pickup coil. What do I mean by a pickup coil? The idea here is this thing right here is supposed to be a coil of wire that's connected to a light bulb. Right now, the light bulb is not lit. Now, I don't know how well these animations work over Zoom, but what I'm going to do next is I'm going to move the magnet towards the coil. When I do that, hopefully you see the light change a little bit. I'm going to move it away. The faster I move it, hopefully you see this, and I'm just going to shake it. If I keep shaking this thing, hopefully you notice that the light is lit on your end of the screen. I know there's tremendous lag. The point being here, notice the following. What was Faraday's law? Let me write that up again. The induced voltage is equal to negative N times the time rate of change of the magnetic flux. What is magnetic flux again? Magnetic flux is something related to the amount of magnetic field lines penetrating a surface. So imagine, whoop, that doesn't go that way. The idea here is some of these magnetic field lines go through the loop and some of them do not. So the number of field lines penetrating the surface of this loop, so if I could shade this here, that would be the surface area of the loop. I know that the magnetic flux in this case is equal to the integral of the B field. Of the B field dotted with the area vector associated with that loop, and then you integrate it. So the idea is you're going to split it up into tiny little chunks and integrate over the whole area. And each of these area vectors, if you recall, points perpendicular to the surface, right? So those are some D area vectors. And these blue lines would be the magnetic field. So let me pause for a second. And let's look at this. Again, The B is the blue arrows. The green is the area of the loop. So in this case, the area of the loop, we could split up into tiny little chunks of area called dA, differential areas. And we see, if you do this integral that I'm enclosing right here, if you do this integral right here, the idea is you add up the dot product between B and dA for this piece, plus the dot product of B plus dA for this piece, plus the integral of B dot dA for this piece. You add those all up and you get the magnetic flux. It's essentially a measure of how much magnetic field penetrates the loop. Once you get that, you could plug that into here. Now, notice we don't get voltage unless the magnetic flux is changing. Right now, there is a lot of magnetic flux going through that loop, but it's not changing. So there's no voltage, so there's no light going on. The idea here is if I move this towards here and change the flux while the change is happening, I see the light. Now I could move this very slowly. If I move it very slowly, the flux is changing, but the flux is not changing very rapidly. Right now, I have a massive flux. This is about as big as the flux will get because the magnet is right next to the loop. All of those field lines are pretty much going right through there. So now what I could do is I could pull this wire, I could pull this magnet away rapidly and you get a large light. So if you change the flux rapidly, you get a lot of light. All right, let's leave it at that. Questions about that? Okay.
I'm not sure if this is correct, but I guess is that kind of an explanation why electric motors have rotating magnets generally? And it's either some brush connection or brushless connection?
So they're related. So
Okay.
the idea here, it's actually, this is actually a detriment to electric motors. This works against motors, and I'll explain why in just a second.
Okay.
But the idea, a motor works on torque. So the difference between these, let me do it like this. So this is an important distinction and is worth spending time on. So a motor, typically, I think that was Corey talking. So Corey, how do you make a motor work? What is the input into a motor?
Well, some kind of force to rotate a magnet.
Usually you have current.
Okay, that's what you meant. Okay.
Yeah, so like that's what you put into the, right? Don't you, or you apply a voltage to a DC motor, which causes current to flow through the motor. And what is the output? What type of energy do you get?
Kinetic.
You get kinetic energy. And so you could rewrite this as electrical energy. And the output is kinetic energy. Well, what is a generator? A generator, what is the input? How does a wind turbine work? If it's sitting there motionless,
kinetic energy is transferred into electrical energy.
Exactly. And so they're the exact opposite. It turns out an AC generator is a DC motor as long as you apply it in reverse or operate it in reverse. So they are very related. The output would be electrical. So now the idea is if you want to understand a motor, that was that problem in chapter 28 point something, where I said, figure out the torque. So we usually care about how much torque you apply to a loop of wire. So the input is current and you have a large magnet sitting near it. Now a generator works a little bit like this. Give me a sec. Here is a generator. The idea is I'm going to put this magnet, this is pretty cheesy, but it works. So here's my loop of wire. No current is flowing in the wire. The reason is the flux is not changing through the loop. There's magnetic flux, there's magnetic field, but there's not a changing magnetic flux. So now I'm going to turn this on. And the idea here is, if I slow this down a little bit, in this case, if I show the magnetic field, notice the flux is going crazy. If I pause this thing, give me a second. Let me, can I jack up the field strength? Okay, right now, how much flux is there through the loop right at this instant? I don't know if you could see that at all. Is it a lot or a little?
Not much.
Not much. There's still a magnetic field there, but I want to point out the magnetic field points this way for the most part, and the area vector is pointing this way. So what's the dot product between those two?
Very little.
Yeah, so B dot dA is approximately equal to 0 right now, right? Because they're perpendicular. Not perfectly, but so what if we step this through a little bit? Now, I don't know if you notice, B and A are almost always perpendicular. So the flux is large. And if I say this is the area vector, which way is the magnetic field pointing? Is it pointing to the right or to the left at the center of the loop? So right at this point, which way is the field pointing?
To the right.
To the right, out of north. So there's the B field. So now I'm going to keep this thing running. Let's keep running. And I'll pause it right there. Notice which way is the B field pointing now?
To the left.
To the left. So I just want to point out that as this thing spins around, the flux is constantly changing from positive to negative to 0 and back again. So what we see is sometimes, let's see if we could plot this. If I was plotting this versus time, this is the magnetic flux. Sometimes it started out at 0, then it became positive, then it becomes 0, then it becomes negative, then it becomes 0. And you could see this, it's basically tracing out a sine wave, right? Let's plug that into our Faraday's law equation. Faraday's law says the induced voltage is negative N, which is the number of turns. In this case, that would be 2, times the change over time of, now this is going to be a little bit complicated, but it's some kind of constant that relates to B and the area, and then maybe some number. I'll just say F or some factor because it's not perfectly perpendicular. But if it was perfectly perpendicular, the factor would be 1. And then there would be some sort of, what is this, sine of omega t. And notice the voltage would end up being something that looks like, in this particular case, negative 2 omega NBA. So I call this the women's NBA theorem. I think it's cosine of omega t. And what we see here is, check this out. If you're very careful and you adjust these numbers just so, this can end up being something like about 180 volts, which corresponds to the wall socket. Now you might be saying, wait, I thought it was 120. Yeah. We'll get to that later. That's peak versus RMS. If you don't know what I'm talking about, who cares? We'll learn that in another chapter. But the idea is, there's how you make electric power. Isn't that crazy? I'm going to pause. Questions?
We had W show up twice here, right? We took a. What did you do to get that second one?
I couldn't hear you. Was that Tom?
Yeah. How did you go from the first to the second equation?
Oh, I took the derivative.
Oh, okay. All right.
Yeah, and then I set the factor to 1. I just said, screw it. Let's assume the B field's perfectly perpendicular, so I set that to 1. And this is not a W, it's actually omega. So even though it looks like the women's NBA, it's actually omega NBA, but yeah. Oh, wait a minute. I should be careful here. Let's leave out that 2, right? Because the 2 was N. I should be very careful there.
Should that be cosine in the top equation then?
What do you mean?
For
It-
the flux?
Well, the derivative of sine is cosine, right?
Oh, yeah. Okay.
Now the other thing here is, depending, you could start this at a different time. If you started it at a different time, you might have got a cosine here. So the actual functions don't matter. Depending where you start the function, you might get a sine or a cosine. So the function in particular doesn't matter, because you're either going to get sine on one or cosine on the other, or you could have a phase angle or whatever. More on that in another chapter. Trey, is that
Okay.
good?
Yeah.
Yeah, you could use either one. Either one's fine. Okay, cool. Now let's think about this. Let's go back to our simple. Okay, so that was kind of jumping ahead, but let's go to this one. The idea here is there's a couple of different things you can do to change the amount of flux. So clearly we could make the magnet stronger. If you use a really weak magnet versus a very strong magnet, there's a different amount of flux. We could also change the number of loops, right? One loop, you basically only get one loop of area. 3 loops, you'd get 3 loops of area. So the number of loops effectively is jacking up your area in this case. Finally, you could increase the area of the loop or decrease the area of the loop. So if you want to have as much flux as possible, you use large area loops, you use large magnets and lots of turns, and then you can get massive amounts of flux. Now check this out carefully. Watch when I bring the magnet towards it. Did you see that? I'm going to move this slowly here. Okay, I'm going to move it towards it again. Watch the polarity of the voltage. Negative. Now watch when I bring this away. Positive. And so we see when I increase flux to the right, I get a voltage which is negative in this case. When I decrease flux to the right, I get a flux which is positive. Whoa. So this is very complicated. What we see then is the sign of the voltage depends on whether the flux is increasing or decreasing. Let me get to some words. So I'm looking at this screen right in here. Lenz's law is the thing that says, it's the minus sign in Faraday's law here. So it says current caused by the induced EMFs travel, I need to fix up the wording here, but travels in a direction by the induced EMF. How about that? Travels in a direction that creates a magnetic field with flux of, what? Do you see all those words? I wish there was a shorter way to say that, people. What? Oh my gosh. Let's get to some examples right now and see what this means. So just to point out, you might hear about Faraday's law. That's this equation. Lenz's law itself is explaining the minus sign in detail, and it's no joke. We already talked about some ways you could do this. There's some different things you could do. You could actually change the area of the wire in a loop by putting part of a loop on a sliding rail, and we'll see that soon. Okay. This is probably my favorite part of the course, everybody. I think you're going to have a good time. There's some other words. Let's read this paragraph right here. We'll come back to the paragraph that we skipped in a few pages. So if a coil of wire is used, the induced EMF sets up an induced current. So I'm going to call that current I induced for the next few problems. The induced current in turn creates an induced magnetic field. Now here's where this gets crazy. You have a magnetic field from the magnet, but you also get a magnetic field from the coil when it runs current. Yeah, I get headaches just from them bumping into my head. All right. Yeah. You'll get, yeah. All right. So let's keep going here. So now this is what I want to talk about. I induced opposes the change in flux. There's a lot of words here. This is very, very complicated. Okay. Let's just do an example. Okay. Let's start with this one right here. So you guys have got 30.1. I'm going to draw it up on my board here. All right, let's focus on what we're doing here. Come on. So we got a loop. This is before. This is after. This is problem number 30.1. I'm just sketching it out on my page so I have it. Okay. Oh, whoops. After there's only one X. All right. Here we go. So let's make sure we get this right. So ask me questions and slow me down if you don't understand what I'm saying. Here's the idea. Suppose you have a single loop of wire, and the idea is before there's an external field pointing into the page. So maybe I have a magnet in my hand and the North Pole is facing this and it's there. Then what I'm going to do is I'm going to pull the magnet backwards, right? And so there's going to be less magnetic field into the page. So again, I start here and I end up out here. So there's the magnet has gone with the North Pole close to it to being the magnet with the North Pole far away. So far, so good. Maybe from this view, it would make more sense. The magnet's close and then I pull it away. So the last picture, it's farther away. Okay. Help me out. In this case, tell me what happened to the magnetic flux. Did it go up or down into the page?
Down.
Yeah, so there's less phi sub b into the page. Does everybody agree with that? Now, the induced voltage wants to create a current that keeps things the way it used to be. What? Just tell me. Start this way. Did I add X's or did I add dots effectively here?
Effectively added dots.
I effectively added a few dots to cancel this out. So the opposite of adding dots would be adding X's. Now just bear with me for a minute. The idea is there used to be 4 X's. Now I only have 1. The loop says, well, I sure wish the current was still there, or I still wish this magnetic field was there, if only I still had 4 X's. So now tell me, which way should current be flowing if I wanted to make these 3 X's and get it back the way it used to be? Clockwise or counterclockwise?
Clockwise.
Right? So the idea is, well, the induced current would want to run this way. How can I tell? Because if I induced ran that way, B induced would be this way, and then I would try to get back to way things used to be. That's, I don't know, questions on that. The induced current tries to keep the magnetic field or replace the magnetic field that was lost, or it opposes any magnetic field that it gained. I should be careful. I just made a mistake. It does not oppose the field. What does it oppose? What's this called?
The flux.
Magnetic flux.
Flux. So we've got to be very careful. Notice the induced current creates a B field that's actually in the same direction as the external field. It is not opposing the external field. It's helping it out. It's opposing the change in flux. See the difference in the sentence? It's not opposing the field. It's pointing the same frickin' way. It's opposing the change in flux. So because I have less phi b into, I induced tries to create B into. All right. You want to try another one? Let's do it. After a few of these, you'll start to get the pattern and we can do the weird stuff. Try this one. Have 2 X's. And we end up with 4. Got it. So here's the before, here's the after. I gained 2 X's. What is the opposite of that action? What kind of B field do I want to add for the loop? Dots or X's?
We want to add 2 dots to cancel out.
That's right. So we see that in this case, opposing the flux is the same thing as opposing the field, but in the last problem, it wasn't the same. Thus why students hate this so much, because sometimes their faulty logic is correct, seeming. Wait, that's not right. Which way is the I induced, I think? Isn't it this way? If I want to make dots, yep. So there we go. So in this case, the I induced is now out of the page. So notice the same magnet in the same orientation could cause an induced current in 2 different directions, depending on whether you're approaching or going away. Let's go to the next one. Ooh. So this one, 30.3. I'm just going to get it marked up. Now we're starting to get a little trickier. So we have 2 X's. That's B external. And there's already present current. So, okay. We're going to come over here to this one. The external is going to flip and be brought closer. Got it. All right, so look carefully on this one. Here, I have an external magnetic field. I also have a loop that's running current. Does this current match this? What do you think? Does the green current? No. Is that okay? Sure. There's no problem with saying there's a loop that has some current in it, and I put a magnet next to it that, so there would be a magnetic field associated with this current, but maybe it's so small we can ignore it compared to this external field from a big neodymium magnet. So if you put a giant magnet near here, who cares about this? The external field is right there. That's what's dominating this situation. Now we go from here to there. Effectively, what have I done to get from this picture to that picture? I added what effectively?
6 dots.
6 dots.
Yes, so
Change.
you're effectively adding 6 dots, 2 to cancel these plus 4. So that's the same thing as flipping the magnet over and bringing it closer. All right, so in this case, what is the induced current going to try to do? I still have this already present current. But what is the induced current going to try to do? Is it going to try to create dots or X's? I added 6 dots.
X's.
Yeah, so this is going to try to make 6. So what direction is that current flow going to be?
going to oppose the already existing one.
Yep. How are people doing on this? Is this making a little bit of sense?
It's getting there.
I'm lost now. Why is there another loop? Like you added more current or something in opposite direction.
This is
the other one. The other one.
It's over here.
Yeah, the red one.
It's the one that's, the red one is the induced current. So let's keep track. This is just the current in the loop. Maybe there's a battery in there and it's running current. Great. Now what I'm saying is if you take a magnet, flip it and bring it closer, for a split second in time, you're actually going to induce a current that opposes the already existing flow. So the induced current will try to cancel this one. It won't succeed, but it'll try.
That's part of the reasoning for why putting magnets next to certain electronics and destroy them is you flip the current and that can damage a circuit.
Yeah, yes.
I'm assuming there's more to it than that.
Yes, there's more to it than
A
that.
lot.
But I would say this, going back to what Corey was saying, think about this. There's motors and generators. Motors are loops of wire that spin near big ass magnets. Motors have an already present current and they start spinning. And as a result, the B field keeps flipping and changing in magnitude. The magnetic flux keeps flipping and changing in magnitude. So the idea here is this is a model of a motor and the coil keeps flipping or the magnet keeps flipping near the coil and that causes induced currents, etc. But one of the things that happens is the faster it flips, the larger this induced current is, and you end up reaching some sort of equilibrium where the motor is trying to twist faster and faster and faster. But as you do that, the motor itself acts like a generator, which opposes its own motion, and it limits the ultimate speed by creating back EMF, back voltage, or an induced current, which opposes the current that's trying to make the motor work. That's what this is a model of. You run current through a motor, it causes a torque, it flips. When it flips, you get a change in the magnetic flux, which induces a current, which opposes the magnet flipping. That'll really get you out there. Isn't that crazy? I love it. I just love it. Because it's, yeah, okay. I should go on to the next problem. I don't know. Questions on that? Nick, did that address your question?
Yes.
Isn't that crazy? All right. Let's take a look at this one. 30.4. All right. So 30.4. What direction is the induced current in this case? So we start out with B equals 0. And now I'm going to add some dots out of the page. So what direction should the induced current run?
To the right.
No current. It's not a circuit. However, let's use that knowledge. So let's see. Do you agree we would try to create X's? Is everybody okay that it would want to try to create X's, right? Now it's not able to do that because it's not a complete circuit. Based on that, which way would current flow in the metal ring if it was actually connected?
Clockwise.
Clockwise.
Yeah. Now, this is where things get crazy. I claim that's equivalent to this being a plus terminal of a battery and this being a negative terminal of a battery. Does that make sense, or am I getting it backwards? What do you think?
That sounds backwards.
Ah, it does sound backwards, doesn't it? But it's not. Isn't that crazy? Let me show you in the solutions, and I bet this will make more sense to you. All right. Think about it like this picture. Does that make more sense to you? The air gap is like the resistor, and the piece of metal itself is the battery. Current flows from the minus terminal to the plus terminal inside the battery. Does that help you, Tom?
Yeah.
Isn't that crazy? Now let's do this. Let's go a little bit slower. Do you agree there would be a very short transient current this way, right? It wouldn't be able to flow across the gap, but we expect that. Well, now what does that mean? If we would need plus charges moving this way, which is the same thing as electrons going this way, and the electrons would pile up on this side of the gap. And so that leaves this side with an excess plus charge. Who knew we were going to talk about chapter 21 today? Isn't that crazy? Doesn't that make you want to just be like so happy? I don't know. I just love it. Yes. Now, Corey is right. If you have enough voltage buildup, you could actually have a spark gap. And then what you do is you create a device called a Tesla coil. And you can have the, okay, blah, 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 blah. So more on that, never.
Can you say that one more time again about the current with the battery at the end there? Because you were saying the current flows in a battery, it flows from.
Yeah. Let's go take a look.
I'm probably just like.
No. So imagine you have a circuit. Let me just draw a quick circuit. Most people have no trouble thinking of this as a battery where that's the plus terminal and that's the minus. And most people would have no trouble saying, well, current's going to flow this way, out of the plus into the minus, right? Are you okay with that?
Yeah.
And then do you agree that current would continue to flow from negative to positive inside?
Mm-hmm.
That's all I was saying.
But then so what's the picture? So the picture at the bottom.
This is the wire. The gap is actually all of this. Just give me a sec. Let me do that in a different color so it stands out. This little gap right here is equivalent to all of this part of the circuit here. The wiring, the resistance, everything except the battery.
Oh, crap. Yeah. I don't know why it is.
Yeah. Well, because it's freaking crazy and I didn't see it either. I'm like, oh shit, I screwed up. And it turns out I didn't screw up. It took me a minute to realize this whole thing that I'm shading in green, you could think of as the battery. These problems are counterintuitive.
Yeah.
Okay. Is that help?
Yeah, definitely. Thank you.
Yep. Okay. Let me see what it's super. Yeah. It's so that's fine. The moral of this little problem is to help you realize what is truly induced is a voltage. If you have a complete circuit, you also get current and it's easier to understand. But now, even if you take a partial loop, if you just take a piece of metal like this and stick it right now, hey, look at this. I'm going to do a flux experiment right here. See this piece of metal? Right now, the Earth's magnetic field is penetrating through this piece of metal. Hey, I just changed the flux. There was an induced voltage there. Now, why am I not getting electrocuted? Because the Earth's magnetic field is about 0.5 Gauss, which is what, 5 times 10 to the minus 5 Tesla, if I did the math right in my head. The Earth's magnetic field is so small, right? It's crazy small. So we don't notice this a lot. But look at all the way around the edge here. If this is all conducting, right? I have a large square loop, a large area, and just turning this thing around, I'm actually getting currents in here. They're just so small, it doesn't really matter. Now, if I put a massive magnet on here, I might be able to detect a slight current there and actually do something with it. But generally speaking, unless you have hundreds of loops of wire and a large magnetic field, these are very negligible induced currents. Okay. The magnetic flux depends on the magnetic field, which is really, really, really weak unless you use massive magnets. So let me go to the equation here. Yeah, collect enough whiteboards and swivel them. You'll have a bunch of tired students swiveling whiteboards and no substantial current. Yeah, you could do that. Let me go back to this equation. In practice, whoops, sorry, wrong way. in practice, oh, there it is right there. The only way you can make this thing substantial is because it relates to the magnetic field. The area of the loop, you can only make things so big and have them be usable, right? You could maybe have a meter of coil or something, a meter squared of area or something, right? But that you're already getting pretty big there. Okay, you could change the angle and change it rapidly. That's one way to do things. You could also use an extremely large rare earth magnet. And then the last thing here is notice the voltage scales with the number of turns. In practice, the easiest thing to do is go to Arizona, dig up a bunch of dirt, get a crap load of copper, and make a lot of wire. Okay, so if you have a lot of wire, you can get a lot of N, you can get a lot of voltage, but you got to be careful. The more wire you use, the more resistance you add from the length of wire. Oh, are we getting into that chapter too? Yeah. Rho L over A. All right. I just love this stuff. It's like all of it in one fun, delicious, conceptually difficult package. Nothing could be more fun to a physicist. All right. So there's that. There's that. This one looks ridiculous, but let's take a look at this one. Now, I just want to point this out. Let's say you have a wire. Somehow, I don't know how, let's say the wire actually stretches and gets hot and increases. Grab that wire. That's right. Grab that wire. No, let's say you have this wire and it increases in size. In this case, this is another example. Did the flux through the loop increase? What do you think?
Yes.
Yes. So which direction is the induced current?
Clockwise.
Clockwise?
Clockwise. Let me think. I gotta think it through. You guys are faster than me. All right, so let me see. It's gonna try and make what, 5 X's, I think. Yeah, and so then it's gonna be clockwise. So notice when this wire gets hot and expands, the induced current opposes the existing current, which slows it down, which reduces the heating, which causes it to shrink back the way it used to be. Once again, we see the natural tendency of these induced currents is to put things back the way they used to be. All right? Yeah. All right, so now here's something. Clearly, this can't be useful, can it? Is there any practical application of this? Whenever I say that, you know there is. What's the practical application of this? Does anybody know?
Slingies.
Interesting. That's not where I was going with it, but that's cool. Sleep apnea. They put you on a bed, they wrap some coils around your chest, they put you in a magnetic field, and as you breathe, you slightly stretch the coils, which they can get a voltage off your chest and get your breathing patterns converted to an electrical signal so you can run signal analysis on it. Trippy, huh? I'm
You
telling
just
you.
explained so much of what I've seen in operating rooms.
Have you? Oh, so you see, yeah, I'm telling
Yeah.
you, it's hard to underestimate. Look at this. You can't see. Oh, yeah. Can you? Look at that. Can you see those tingly bumps all over? Well, if not, you can see a bunch of ugly white fur. Oh, man. I'm seriously tingly all over. Nothing is as important as this topic ever, or this lemonade. I'm telling you. You could use this for pickups on a guitar. You could use this for all kinds of measurement tools, right? So anytime you have a tool, you could attach a magnet to something or a coil of wire to something and a magnet nearby. And next thing you know, there's going to be a change in flux and you could get this massive, well, maybe it's not massive, but you can get a voltage. I saw, John Garrity. If you don't, he's a frick genius, man. This guy, he showed me this link for something, or maybe I forget who it was, but it was somebody that basically you could just basically make your own EKG machine at home using like a cheap O-scope that you could buy off the internet, and then you just get some coils of wire and blah, blah. Anyways, so it's like, oh my gosh, the applications of this chapter are insane. It's super useful. That said, let's get back to some content. All right. Yeah. Transformers are a huge deal. Let's look at transformers really quick. Let's have some fun. All right. For once, let's enjoy this class. Wait, where did that go? Oh, here it is. This is the link I gave you guys earlier. Let's look at how a transformer. Oh, let's look at an no, let's not do that. Let's do this. So where do I want to go with this one? All right, let's go to here. Here we go. So the idea right now, if I move this thing rapidly, I get light. And the idea is by changing the position of these two things, I'm changing the magnetic flux and I get light in the bulb. Now I'm going to bring this really close. Now I just want to point this out. When I put these two things right on top of each other, I don't see anything changing. The magnetic flux is what? Big or small right now?
Pretty big, right?
Enormous. The coils are right on top of each other. This is a huge flux. Now watch what happens if I turn this off. Oh, I switch the polarity. I see. So it doesn't go to zero, it switches. But the idea is you can do this. What if instead of connecting it to DC power, look up here. DC power is a battery. I'm going to connect it to AC power, which is like the wall socket. When I do that, the idea is, whoops, let me get this close, but not quite inside there. The idea is the current in the primary, which is the thing. Let me get my annotator. I hate annotating in Zoom. This coil right now is called the primary. So I'm just going to put a P next to that. This one is called the secondary. This is called the AC source. It's basically a wall socket. Okay. We have an AC source voltage. We will learn more about this in chapter 31. So don't try to get too far ahead of yourself here. But the idea is we're changing the flux. If I could, give me just a second. Oh, I hit the wrong button. Gosh. Let me see. Hold on. Let me go back. We can get this. Still going. Let me get this thing out of here for a second. I hit the wrong button. Okay. Okay. So right now, I just want to point this out. Let's see. Which way is the current moving in the coil? Which actually, okay, let's be careful, people. What I'm going to do is I want you to look at this electron right here. Okay. And I want you to watch it when I step this thing forward one step. Here it goes. Whoops. Okay. That electron is moving upwards. So which way is the current in this wire?
Downwards.
That's right. So if the electrons are moving up, all of these have the current moving downwards, right? Because electrons moving up is the same as current flowing down. So based on that, this coil right here is effectively a bar magnet, but which side of it is north?
The right side.
This way. Because the B field created by it is going out of north like that. Think about it. If you grab that wire, this is B external, right? And what do I mean by B external? It's external to the secondary. This is the primary. This is the secondary. So the primary magnetic field is external to the secondary. It's created by something external to the secondary. So now notice over here, the B field is going into the page. So now what direction should current flow for these jobbers? Should it flow up or down in that spot?
Well, if it's going to oppose it, right, it would go up, correct?
Okay. And that means the electrons should be moving
Downward.
Let's see. Now we're getting close to the maximum. We may have already passed it. So I'm going to hit step. Did you see it move down a little bit? They did. So now just watch the motion of the electrons. There's a little bit of a lag there. And notice these electrons don't move as much. The electrons in the secondary, the larger coil, do not move as fast as the electrons in the primary. And that's because the power transfer isn't perfect. But what we could do is jack up the amplitude, and it's more dramatic. And so notice the complicated pictures that we were drawing on the board with these dots and these X's are supposed to represent the B field going into the page, then out of the page, then into the page, then out of the page, like this. And so what you do is you get this crazy induced current, and we can use that. Maybe you've seen these silly little things where you put your phone on top of something and you get it to charge wirelessly. How does that work? Like this. What about, give me a second.
It reminds me of the article I read in Disney made, I guess, a wireless charger using a giant copper pole in the middle of a room.
Hello. Hello. What have we here? What have we here? A cheesy little toothbrush. What do you think this stupid thing is? It's a piece of iron. There's a bunch of coils of wire. You plug it into the AC wall socket, and that charges your toothbrush. Oh my gosh.
Oh my god.
This is your toothbrush, you cretin. Take this and put it in the bathroom. Okay, I got to get back to work. That's actually my job.
Daddy, why did you do that?
I just showed them a toothbrush. I got to get back to work. Okay. All right. Yeah, that's how toothbrush works. All right, great. You could also just scrub and make sure you get those gums. All right. All right. My mom was a dental hygienist. If I didn't say away from the gums, I'd be in trouble. Okay. So next, what were we doing? Yeah, you could do anything with induction, right? So there's induction heating stoves, right? How does that work? Well, you have a big coil of wire and you generate a magnetic field going up into the pan, and then you flip it back and forth. The bottom of the pan's got a coil that gets hot, and then that's basically a transformer where one of the pan is the secondary. It's the same thing. So when you start looking around and see this stuff, it's like, there's a lot of applications of this.
Wait, is that the type of stove where like? No, is that the one where like
it looks like a plate of glass?
Yeah, and when you take off the pan, the thing actually isn't hot, so like that's why it's like more safe.
Exactly. And it's,
wow, that's
right?
crazy. That's so funny. Now when I see that, that's cool.
Now there actually is a little bit of heat because the pan gets hot
and
then it's touching, and so it transfers some of the heat back through contact, but the glass is not a good thermal conductor, so it's not efficient at transferring. So it's very efficient at transferring the electric energy into the pan. It heats up the pan well, and then the transfer is by thermal contact by physics 162 down back to the glass.
Less. That's why it's less than like just a regular burner, obviously. Wow, that's cool.
Yeah, that's interesting, Tom. I have no idea. Is that a thing? And oh yeah, that's cool. There's a weird thing too related to this class. Have you ever seen those table saws where you could put a hot dog, and as soon as the blade cuts the hot dog, it immediately drops below and keeps from cutting the hot dog?
Saw stop.
Yeah. And so that, I think, is a capacitance measurement, or is it one of these? But you could look that up. It's something that we've covered in this class. And you could say, how do those saws work, and how do they know to drop and not chop off your finger? And it's either going to be a capacitance measurement or this. So I'm not sure which it is. So you guys can check that out. It is super cool. Their worst way to cut hot dogs. Yeah. All right. Let's see here. Let me get back into the class here. What were we doing here? Oh yeah. Check this out. You could also jack up the frequency, and that's going to make these lights a little brighter. So we get this cool light. All right. That's enough of that thing. Let me stop this madness. Ah, that's better.
So does this have anything to do, so like with that light, how it's flashing like that? Does
Not
this
sure
is
about
probably,
that one, Corey. Not sure. Okay. But go ahead. Go ahead.
this is probably something that is like, it's probably not related, but like, you know how like when there's football games and they do a slow motion of someone catching like a pass or something, and
Okay.
you'll obviously see that the lights are flicker, like they're quote unquote like flashing because
That's
it saves
probably a
power
refresh rate.
when it's flashing at that rate.
Yeah, that's just dissimilar refresh rates. So the idea there is right now, my computer's refresh rate is probably 60 or 75 or 50. One of those numbers is usually it. And so cameras can shoot at different speeds. And so the idea is, let's say you're running a screen and it's refreshing at a certain rate. That might be the case. Or if you have
That
lights,
makes sense now. So it's the screen. Yeah. Okay.
or it could be this. It could be lights are shining on an object and the lights are turning on and off 60 times a second. Actually, 120 times, because the voltage goes positive, the light turns on. The voltage goes negative, it also turns on. And if it's going at 60 hertz, then it's actually going to two maxima in 60 times per second. So 120 times per second, it's turning on and off. So now what if you're shooting the camera at 39 frames per second or 29 or something, right? Or 109, some number that's not an even multiple of 30. What will happen is you'll get the lights in the room are turning brighter and dimmer at the same time as you're taking photos. Or maybe you've been driving on the side of the road and it looks like the hubcaps are going backwards. Same thing.
Yeah. Okay, gotcha.
All of those are the same.
But is that a thing like you were talking about where it's like the lights, you know, it's not like the light is actually quote unquote like on continually?
Yeah, that there could be a number of things involved, so I'm not sure. How do I say it like that? Yeah. Now, one of these things is aliasing. If you've ever looked at pictures and it looks like there's a bunch of stripes on it, that's called spatial aliasing. If you look at the hubcaps, that's called temporal aliasing, where it's the time is refreshing at different rates. And so that could be the same thing as the lights. The other thing is you literally could have something weird, something else that I don't know about. So yeah.
Cool. Thank you.
Yeah. All right. So yeah, and a lot of times what you'll do, and this might have been what Corey's comment about the strobe light might have been going for, but the idea is if you could put a strobe light on something, what you could do is you could dial in the strobe light, and when it looks like the thing has stopped moving, you know that your strobe light and the thing that's spinning are at an integer multiple of each other's rotation rates. It's not necessarily the same rotation rate, but if you keep going down and down and down, the lowest frequency where it looks like it stops, they must be matched frequencies. So we used to do this in the science night with a fan, and we'd put different colored dots. And you could do some tricks where it looks like if you turn it to, let's say the fan's turning at 100 hertz. If you have it rotated 80, it looks like the dots are shifting by 1/5 of a perimeter every time. And so you can get the dots going backwards or forwards. And it's pretty fun. I'll show you sometime when we're in school together, which will be never. So, all right. So, oh my gosh, there's so much fun stuff in here. Sorry, this class is so boring. All right, so let's go to here. All right, I'm gonna let you guys try this one at home, 30.6. This one, blah, 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 blah. Okay, so this one is cool. Now, what I'm gonna do here is maybe just give you something really quick in the chat. Let me find it really quick, hold on. Girls, out of here, let's go. All right, videos. Playlists. Is this the right one? No, this is the wrong one. I got to go to a different channel. Sorry. This one. Okay. Is this the one? Oh, now I got to hit this button. So slow. So if you want to just see the fun stuff, here's all the fun stuff. And I'll put this link in the chat if I can move my Zoom around correctly. So this is like all the fun demos that I was not able to do in class, like the jumping ring or just moving a magnet near a coil of wire that you could actually look at, dropping the magnet down the tube, the eddy current, flashlight, the pedal, all these different things. There's the toothbrush. How does a microphone work? Oh my gosh, there's so many things. Seismographs, that's pretty cool. Let me get this in the chat before I forget. So if you want to look at these and just have fun, there's some simple examples, all right? And there's some crazy ones in here. I tried to link these in the solutions at the questions where they appear. So just in case that doesn't work, I'm giving you that playlist. All right. So that said, I hate showing videos in here, but I'll just show part of one just so you can see the setup. We're not watching this whole video. So here's the idea. Let me make this big. All right. So in this example, there's some coils of wire right there. I don't know if you could see them. They're connected to this thing, which is called a variac, which goes to the wall socket. So this goes into the wall socket. And the idea is this is actually going to produce AC current. So what's going to happen is every once in a while, the current's flowing this way and you get a B field upwards. And then a second later, or a fraction of a second later, it's going to be flowing the other way. And so you're either going to get B fields that alternate. So you're going to have a B field up, then a B field down, then a B field up, then a B field down, et cetera, et cetera. Now, Bobby can't see that at all. So you're going to have a B field up or a B field down, B field up or a B field down. The idea is you're trying to let the current oscillate. And as a result, you're going to get a magnetic field up and down. Now this, let me get a different color here. This black thing actually goes all the way through to right here. And so that is just, it's called piano wire. It's basically soft iron. It's a piece of iron, and it's a particular type of iron called soft iron. Soft meaning easily magnetized, meaning you can put a magnet near it and it will magnetize rapidly. And then you can pull the magnet away and you can flip it and it will flip. So it's easy to magnetize. All right. So the idea,
is it a solid cylinder?
Yeah, it's just tons of wires packed in there. So if you pull it out, it's basically from the top, it would look like this. And there's just hundreds of wires shoved in there, crammed in, and then shrink wrapped.
Oh, okay.
So it's basically just a whole bunch of wires like this all over, and then you shrink wrap them and pack them into a tight cylinder. So it's a solid piece of iron made out of wires. Is that good?
Yeah.
All right. So now the idea is this piece of iron can take the magnetic field from the coil and multiply it by a factor of 500 to perhaps 5,000. So what this does is the iron by itself is not a magnet, but when you put this coil of wire around it, that's a solenoid right there. That's a solenoid. The solenoid will energize. And when the solenoid energizes, the magnetic field gets bigger by a factor of 5,000 because of this piece of soft iron. Maybe it's only 500. I don't know, but it's some large factor. Okay. Now let's step through this a little bit. Boring, boring. Oh, there's the view. So it's just, I don't know if you could see, but there's a bunch of little. Okay, there it is. All right. Okay, so now what I'm doing here is I'm turning up the voltage. So, whoops, you can't see that at all. I'm going to take this voltage and I turned it from 0 up. Oh, geez. Instead of 0 volts, maybe I'm going up to about 20 volts AC. And more on that in a minute. And what we see here is this is just a piece of aluminum. The idea here is when I turn the voltage on, there's a large magnetic flux through the aluminum ring. Oh, geez. Come on. I'm having trouble with my colors right now. There's a large magnetic flux through the ring. And I don't know if it's up or down. It's going to change. But the idea at one instant in time, maybe we get this large magnetic flux. And so at that instant in time, maybe the field, the current runs this way in the wire. So that would be I induced. And that opposes that flux. A half second later, the magnetic field flips from the rod, and that will also flip the direction of current in the coil. As a result, this coil creates a magnetic field, which is constantly opposing this magnetic field, and it levitates. There's no wires. And it, all right, let's leave it at that. So now there's, I'm sorry if that video doesn't work. My apologies if that didn't work for you. But the idea is, let's look at this problem. It's a little bit less dry now to look at this problem. are right here. So this is supposed to be a schematic of that demonstration. So the demonstration I just tried to show you and probably failed, but the idea here is this is an aluminum ring. And this right here, this inner thing is that solenoid, right? So this is the solenoid. And then there's the iron core as well. So the idea is if you turn on the solenoid right now, let's see, which would you get, a dot or an X from this arrow? Let's see, I think that would be an X. So the solenoid is going to create a B external into the page. As a result, the current induced is going to oppose that change. It's not always opposing the change in the field, but it's opposing the change in the flux. All right. So, excuse me, it's not always opposing the field. It's opposing the change in flux. In this case, they happen to match up. So there we go. And the idea here is we see that the current is going to run the other way in this one. And so as a result, why does this thing levitate? Let's go to the solutions. I don't know if I'm going too fast here. I'm getting a little bit excited. The idea is it's supposed to look like this. The ring levitates because if you look at it carefully, the solenoid looks like a bar magnet pointed which way. So if I was looking at this thing, is the North Pole on top or on bottom of the solenoid at this view?
On the bottom.
North and south. Then I'm trying to put this other magnet right next to it. Whoops, that's not good. Let's say I'm trying to put that other magnet right here. And for this one, which way is north? That way. And so they are repelled. Now, I guess really what it looks like is, I don't know if you remember, the solenoid was really big going this way. So it's actually probably slightly better to model it like the magnet is just above, where this is south and this is north. And the idea is the loop right here is supposed to be this thing, and it gets pushed away and it levitates up. So that is what's happening here. That's a lot of arrows and stuff to understand. Let me pause. Are there any questions about all these arrows? This is supposed to be B induced. This right here is I induced. This is supposed to be B of the solenoid, and this is I in the solenoid, if that helps. All right. So I have no idea if this is going over at all. So I'm going to show you a couple of things. And I think the videos are probably better for you to watch at home, because then you can pause it and kind of digest it at your own. So I just want to point out there's a bunch of words here. You can read that. Notice we're going to come back to this in the next chapter. That's why I'm okay moving on. But there's a video for this one, and I gave you really good solutions. There's a video for this one, and I gave you really good solutions. So I'm going to let you do those at home. And the idea is I expect you to watch those videos, try and understand all the frickin' arrows that you see. And again, watch this video and try and understand all these things. All right. And yeah, let's go ahead and stop that for a second. Any questions right now? There's a lot of conceptual questions that I'd like to ask about this, especially on your final exam. They're difficult too if you don't practice. If we have a ring with current that is in the same plane as another ring with an, yes, exactly, Alexis, I agree. You have to read carefully and draw lots of pictures and draw lots of arrows. If you try to get lazy and not do them, you almost always screw it up. Yeah. This eddy current breaking is another one. Let me show you one last video, part of a video. I don't know. I can't help it. These are my favorite demos, so I'm going to take a little latitude here. Let's look at this one here. It's a short one. And I know videos don't work too well on Zoom, but just give me a second. Oops. So the idea here is we put some skateboard bearings up here. So right here, there's some skateboard bearings. And so the idea is there's pretty low friction and these things are just going to swing back and forth. Notice, I don't know if you can see this, there's some slits here. Okay. Whereas this other one has no slits. So this is a solid disc down there. This one's a slotted disc. Whoa, what is happening? My computer. All right. Well, all right. I'm going to give up on that. The idea is that the one with slots in it, I'll let you watch the video later and see, but it turns out the slots in the disc affect the motion. And it relates to some problem that we already did today. I don't know which one. But you can kind of take your guess and see what happens when you watch that video. This idea, it turns out when a piece of copper swings through a magnet, all of a sudden what you have done is you have increased the magnetic flux through the piece of copper. That causes an opposing magnetic field to be produced by the copper itself, and that causes magnetic drag or magnetic braking. And so the copper swinging through this piece of magnet, even though copper is not magnetic, the induced currents are large, and you will see this copper disc slow down due to the magnet. So that's a magnetic dashpot or a magnetic damper. And you could actually do this with a train. You could take an electromagnet and point it straight at the rails and run a massive current through this electromagnet, which produces a massive magnetic field that goes into the rails on the train. And as the train moves, each new piece of track is getting a massive magnetic flux shoved into it. So you get eddy current braking, and you could slow down a train with magnetic brakes that way. It's kind of crazy. So that's one way you could actually, instead of having brake pads, you could have magnetic braking. If you have a hybrid vehicle, I wonder if there's some way that you could use the braking force to recharge your vehicle while you drive. As you hit the brakes, you could have induced currents recharge your battery. So that's something you could do in a hybrid. I'll let you read about that. We better take a break here, and not just a magnetic break, a real break. So let's come back at 5:55. All right. So let's take a short break, and then we'll do some more problems where we're actually crunching the numbers. All right. Still got a couple minutes here. So most of you are all either done with physics or you're never going to have me again. I'm just curious, if you could choose how I taught Physics 161 next semester, based on your experience with online classes and ERT mode, not that I'm going to take your recommendations if I, can't do it physically, but what would you choose for those students if you could choose? Does anybody have any strong feelings about what type of structure you would give the class?
I tutor 161. Is my mic on? Doesn't say.
Yep,
Yeah,
I
it
could
is.
hear you. I could hear you.
Geometry seems to be a really big struggle point for a lot of students. It's just
Oh, sure.
they don't understand how the problems even start, so they fail the rest of the class because they don't even know how it begins.
Sure.
But
I guess I
that's
was
hard.
thinking more of in terms of the structure, like how many exams, how many quizzes, what kinds, that kind of stuff. If you could make because this class, you guys are already screwed, right? This class is already over. But if you could design your class, obviously you don't know what it takes to do the stuff behind the scenes, but if you could do it however you wanted, what would you do?
Personally, I would like somewhere between what we had before and what we have now. Like a little bit less frequency, like maybe every other week we have an exam, but every week.
A quiz or an exam?
Yeah, a quiz or an exam, I guess.
So like a quiz every other week, say every 2
like
chapters?
every other week with larger chapters. I think that might help with just kind of giving people more of a chance to space things out.
What about exams? How many exams would you want? One final plus a bunch of quizzes, or
at least one other exam, just so we really get a good feeling for how you grade an exam and how you administer an exam. But I know at least with Youngblood, it took a couple of tries to really figure out what kind of questions he would ask and how things would look.
Sure. Hopefully with my class, it won't be as bad because you've got like 4 practice exams of each set of content, right? So you could see mine a little better.
Yeah, exactly.
Hopefully that'll help. So Braden, you say 3 exams and a final. So now, Braden, if I did that, there would be 0 quizzes. Would you like that more?
Yeah, I think I prefer that a little bit more. It's just the structure that I've been used to in all of my other classes. And it's just like, with this class, it's a little bit like, am I going to pass or not? Like, I know the final is worth a lot of points.
Right.
And with my other classes, I like already know like if I am going to pass or fail those ones, and this one is kind of like up in the air up until
sure
I take that.
Most physics classes, the final exam is usually worth at least 30%. So usually you don't know your final grade, but oftentimes you could tell a little bit more if you're going to pass or not, right? Yeah. So interesting. Now, if we do exams, what do you think is the best way to ensure academic integrity for 3 exams and a final? What have your teachers done that you feel like is most reasonable to ensure that?
Well, at least for the statics class, he just makes us turn on all of our cameras and he allows us to use our notes, but he switches around between students, just checking on them, making sure that they don't have their phones out. You have to have your camera pointed towards yourself the whole time.
Which, of course, do you agree that's about as easy as possible to game? Anybody that really wanted to could totally game that, is my thought.
Yeah.
Because you could draw a picture. I've heard about students that literally draw a picture of a phone, and you just have this picture of a phone sitting there, and the person on the other side can't tell. You draw a picture and put it on a big eraser and put a little Apple logo on it. There's my phone. Right. So to me, that's like total bullshit, right? There's no academic integrity with that whatsoever. That's just my opinion, right? I don't know. So is there some other way you would ensure the academic integrity of those?
One thing Cisco does, the networking company, is they will, right now they're administering online exams for the CCNA, and they do that where they have you keep a camera on the entire time, but before the exam, they have you show them your entire room through pictures, and you have to send them right as you start the exam, so you don't have a time to move and change anything. So like you show them your desk, you're like what's in your closet, you make sure no one's in the room.
Do you feel that's too creepy? To me, so I'm too picky, because for me, that's like the opposite end where it's like, that's just too freaking creepy. That's where I'm torn, is like, I kind of like like just assuming students will do the right thing is the stupidest thing ever, right? Students are going to cheat the fuck off everything if they can. That's what students do, right? If students can cheat easily, they will. No question. I've seen that everywhere, time and again. But if you make it too hard, you're like spying on people, and I hate it. That's what I don't know.
In my
I think
personal
it's-
experience. Oh, sorry. Go ahead, Corey.
Go ahead.
I was just gonna say I think it's reasonable just because they know ahead of time you're going to want to see the room. So if there's anything personal you don't want people to see, you have an opportunity to remove it.
Okay.
But I still see why it's kind of intrusive. Like, let me see the room.
Yeah. I don't know. What were you gonna say, Ryan?
I was saying, in my personal experience, with all of your exams in person and online, or whatever you do, everything you do, because even in person, you would have like different versions of the test, and we'd talk about, us classmates, we'd talk about it afterwards. And like, if you don't know your crap front and back going into your exams, no matter what, you will not be okay. And that small amount of exam time that you have, if you didn't know that material, is not any way possible for you to like try to, like cheat or Google something or look it up. How do I find this? It's like, if you don't know it already, it's like you're pretty much already screwed.
You're
no matter
slow.
what.
You're slow, right?
Yeah, you're super slow, and you get like nothing done.
Yeah. Claudia, what did you think? I saw you kind of shaking your head when we were talking about the spy cams. What do you think about that?
That's a little too creepy. I want some privacy in my life.
Yeah.
But I agree with who was it right now?
That was Ryan.
Yeah, with Ryan. Like, if you don't know what the heck is going on those quizzes, you just don't know.
Yeah. Oh, let's see. Yeah. How many exams versions do you think I would need to keep people honest on a take home? Obviously, if every single student had a unique exam, it would be impossible for people to cheat because you'd have a unique exam.
But impossible for you to grade.
It's also impossible for me to create in a timely manner. As I've discovered with this giant stack of papers I have behind here, which is your exams, I've got this pile of versions and it's getting insane. But yeah, so you guys are not going to be able to cheat on your finals. I can tell you that. But I'm just curious. Obviously, if you only create 2 versions, people are going to cheat like hell. If you create 4 versions, probably. How many do you think you need to keep people honest in a class of 60?
You could make it statistically advantageous to bank on cheating. So if you know about how many students you have per semester, you could say like, well, I want there to be a less than like a 1 in 4 or 1 in 3 chance of getting it right, and make tests accordingly.
Yeah, well, that's why
that's still a lot.
Yeah, that's why I have multiple choice questions with 12 answers or 8 answers or something, right? So I'm just catching up on the chat. We should probably get back into this thing. Aldair, what do you mean by 4? Oh, I see. That's the number of versions you're thinking, 4 or 5. I think it's got to be at least 5. Number of people divided by 10 or something. Yeah, somewhere in there, right? Like for this size class, well, you guys have got a lot more than 4 or 5. So we may end up with 26 versions. So we'll see. But yeah, generating the solutions is a nightmare, I've discovered. But I've already committed. So the number of possibilities is actually... Like if I have 8 versions per problem and 15 questions, think about that. That's a lot. So what is that? 8 to the 15th? Yeah.
Yeah, maybe it would be worthwhile to spend the time trying to digitize more of this to where you could set up a computer program that has basic types of problems and you could just change some of the values and get a different answer. Like that might save you a lot of time long run if you were willing to do that.
That's the Canvas solution that we have right now, which is infuriating. It takes a long time to code those, and you can see I don't have very good success when I'm coding. Like I'm just counting the days. It takes me, by the time I'm done, it'll be at least 10 days to create your finals, let alone grade them and do the oral exam. So we're talking like 15 work days just for one test. That's a lot of time. Yeah. Yeah, I like that one. Go back in person.
Right, the person.
That would be...
I think for an exam day, that could make sense. Like divide us through 2 rooms and you walk between 2 rooms.
I have asked about that, but the school is not willing to do that. So Now maybe they'll change their mind, but because that was what I first proposed for this fall, so that you guys would have normal test days. But the idea is they say you have to have the online option, and as soon as they do that, I'm stuck. They say as long as one of the sections is online, you could teach your class in person. But since I'm the only one teaching the course, yeah, I thought about that, and I just don't know. I don't like the idea of asking anybody to do something where they might kill their parents. That's basically it, right? I don't care how shitty it is for me. I just don't like the idea of asking somebody to kill their relatives. And I know it's unlikely, but it's like,
What if it happened?
it would be such a catastrophic risk that to me, it's like, I'd rather have a shitty class than have people die on my watch.
It's trying to sleep at night because a test killed someone.
Yeah, it's like, man, I'd rather just pass a few more people. So you guys are going to get lucky, and maybe I'll be nice to you. Maybe.
Quick interruption.
Sure.
My chem class, we kind of do that. So what we've been doing for the past semester is that we have labs in person. So, but it's only 5 of us at a time. And then we just took a test today, and it's only 5. But the only thing with that is that it does take us 2 weeks to take a test.
Yeah, you could split that up. Now, in that one, what happens if a student doesn't want to do the labs in person?
There's not really an option. I'm pretty sure everybody's going to the labs.
Yeah, I think the school, well, I don't know. I'll check in with them. But yeah, the challenge with that one is then you have to teach online labs and in-person labs simultaneously, which is also, that's also a challenge. Oh shit. But yeah, I mean, I don't know. Maybe that's the way to do it. Just
Maybe
cycle
you could
people
wear
through.
like a GoPro or have like a camera streaming on YouTube for people that don't want to go to the lab but want to be a part of lab. I don't know.
I don't know. It's just,
Who knows?
There's probably, all right, we should probably, I tell you what, it's been 15 minutes. We should do some more problems. If you guys have deep thoughts, send me an email. All right. I'm open to hearing thoughts, and I'll follow through on any leads, but at some point I got to just pull the trigger and start prepping that class. Of course, it'd be nice to get your finals and my other finals done first, but all right. Anyways, let's not do that. Let's get rid of that. I don't know. I appreciate you guys. Those are great thoughts, all of you. And I don't know. It's just nothing is great here. Let's see. Let's get rid of that. I want to get to this. All right. Motional EMF here. So, all right. Getting back on topic here. So, this arrow is really big. Let's see if we can narrow that down. So this, if you want to get emotional, this is what I'm talking about here. Let's say you have a rod and it's moving in a magnetic field. Forget all these words. You have a neutral rod. Assume the external magnetic field is lined with either I, J, or K hat. Okay. We see that when this conducting metal rod, the metal rod is a conductor, when it falls down, the electrons end up over on this end. What direction is the magnetic field pointing? The external magnetic field. Let's start simpler. Which direction is the force on the electron if it ends up over here?
To the left.
So if the force is this way, which way is this charge moving initially? It's in the rod.
It's moving down.
Down. So what direction is B external?
Out of P?
Let me see. V goes to B. No, I think it's into the page, right? Because it's an electron, it flips. V goes down.
Oh, yeah.
V goes down. B field into the page. My thumb points towards the protons, but because it's an electron, it flips. So the idea here is, see if this makes sense to you. What did I just say? Into the page? Whoops. Let me get my eraser here. So what I'm saying here is, if B external for this scenario points into the page, I claim there is a force to the left on the electron. Everybody double check that. Line up your fingers with V, curl them to B. My thumb points to the right. I flip it because it's an electron and I get the correct force. All right. So now that sounds good. Now, part B. As the rod falls, it speeds up. What's going to happen to this rod as it speeds up in terms of the charges?
More charges get separated.
We're going to have more and more charge separation. And so the idea is we'll end up with more electrons leaving the left end of the rod, or sorry, the right end of the rod, and ending up on the left end. So as a result, we get this net migration of the electrons from the right end to the left end. What would be different if this problem was a moving rod made of glass?
Nothing.
Nothing really. Maybe you would get less charge separation, right? That's one thing, but we'd still expect electrons would pile up on the left side, which would leave an excess of protons on the other side. So the idea is if this was made of glass, the same thing would happen, but to a lesser degree. That's all, because the glass doesn't conduct as well. The electrons are not as free to move. But you could drop any piece of material in the world. And think about this. In the real world, there's the Earth's magnetic field. So right now, but if I move my finger downwards, there's a magnetic field penetrating here. This is a very bad conductor, but you could actually induce a voltage across this conductor. It's going to be tiny, but you could do that. If you have a piece of metal, it's more likely to be effective. So if you care, let's see how this can be useful. So the size of this thing, the size of the induced EMF, sometimes called a motional EMF, is the amount of magnetic field perpendicular to the motion times the length of the rod times the speed. So if we go down into here, here's the idea. We're now going to take a system where these lines that I'm drawing right here, these are rails, okay? And the idea is I'm going to put a rod on top of those rails. If it helps, I'll show you a quick, I have a simulation of this where I'll just show you what it looks like in the real world. Whoa. So it would be something like this. And I don't want to spend all day on this video here, just show you the idea. So the idea, oh, let me scoot forward a little bit. Whoops. Oh my gosh, come on. Okay. There. So that's the idea, is these are the rails right here. So these are long pieces of metal right here and right there under my arm. Now I'm putting a rod right here across this. And the idea is the ends of the rod, or sorry, the ends of the rails are connected by this device right here. So this is like the resistor in the photo that I'm about to show. So if I could step back just a little bit here so you could see it a little bit. Annotating in Zoom is such a nightmare. There we go. You can see this a little bit better. So again, this is a rail. This on the other side is one of those other rails. And when I take this rod right here, and I'm going to place it across there, I connect the circuit. And so what we see is there's actually magnets in here. And so as I move this thing, it actually looks a lot like this problem right here, where I know it doesn't look quite the same, but again, these are the rails right here. And then I was going to take the rod and put it on there. And this was that measuring device. So the idea is I could take the rod and I could pull it very rapidly this way, and you actually see a current. That video, you could see it's a tiny little current. It's like a microamp, but it does actually work. Okay. So that said, you can learn a lot about these problems, and they're worth doing for this reason. All right. Whoops. So let's look at this one. I'm going to draw it up on the board. I tried to help you visualize it. My apologies if that was a bad visual. I'm going to draw it up and then we'll work on this one. Okay. Okay. This is 30.11. All right. So we've got a resistor here. There's an external field. Okay. All right. And so just to label this, let's call this B external. What else is in there? I'm just going to write down the facts here, and then I'll share my board here. So it says R is equal to 4. V is 10.0 meters per second. It's pulled by a force which has unknown magnitude. Yeah. The length is 20.0 centimeter. And then, B external has magnitude 500 millitesla. So that's actually a pretty big field. That's half a Tesla. Some MRI machines use that size field. So this is enormous. It's like 1,000 times the Earth's magnetic field. So that's huge. Okay. So I've got this problem here. I don't need this anymore. All right. So in this case, let's think about what happens. We're pulling this thing this way with this speed V, and it has length L. And what are we supposed to figure out here? Did it say? Let me read. Determine the motional EMF. So let's get E motional here. So E motional is equal to B perpendicular to the loop, or perpendicular to the rod, excuse me, times its length times its speed. Well, in this case, I think we know all those things. We know the external field, we know the length, and we know the speed. Check. We've got this. So that's part A. It's basically plug in some numbers. I think you can do that. Let's leave it at this for right now. In this particular case, what is B perpendicular? All of it, because all of the field is perpendicular to the rod. Okay. So for this case, that'll just become B external. Again, because B perpendicular happens to be all of it. Part B says, determine the current that flows. So here's the trick on this. We're going to pull this. These rails are not connected at this end, but by pulling this thing, it acts like the battery for the circuit. When I move this rod in the presence of that magnetic field, it's going to act like a battery with this voltage, similar to the induced EMF that we saw earlier. So this rod is like the battery with this voltage. So in that case, how much current is going to flow? How would I do that? How do you get the current?
V divided by R.
Yeah, and what's the V?
Oops. The one that we just figured out. Is that right?
Okay, yeah. So I think I just want to make clear, when you say V, do you mean speed?
Oh, sorry, no, voltage.
Yeah, so that's now we see one of the advantages of using the letter E, right? He meant delta V equals IR. Well, I is equal to delta V over R, which is just B L V divided by the resistance. Cool. So now we have an idea of how much current is going to run here. And I bet the next question is which direction that current flows, right? What do you think? When you pull the rod this way, what are you doing to the magnetic flux through the loop? Are you adding dots, taking away dots, adding X's? What? You pull the rod this way.
Adding dots.
You would be adding dots if it moves that way. So now the induced current should try to create what?
X's.
So which way is the induced current? Clockwise or counterclockwise? This way? What is that?
Clockwise?
Clockwise. So now instead of just saying, oh, there's a current, we have a number for the current and a direction. All right. So now, great. So C, let's just say, what did I say? What did it say? So we said it was clockwise, I think, right? Okay, next question. So part D, determine the magnetic force due to that induced current. So there's going to be a force on this wire. If you had to guess, which direction is the magnetic force on the wire going to be? I'm pulling it to the right. Is this a magnetic braking problem or a magnetic make you go faster problem?
Braking problem.
Magnetic braking problem. All of these are going to be magnetic braking problems. So generally speaking, the magnetic force should have at least some component that opposes it. So I suspect the magnetic force should be this way, but we'll find that out in a minute. Does that make sense? I goes to B. Yes. I goes to B external, goes this way. So remember, the external magnetic field is the one that causes a force on the induced current. The induced field cannot cause a force on itself yet. All right. So we could tell the direction. I think that's actually part something. That might have been part E. Part D says, how do we get the magnitude of the force? What's the equation for the magnetic force? I L cross B external. Right? Now, I don't need to do an integral here because the magnetic field is uniform. If the magnetic field was non-uniform, blech. All right. So in this case, I think we know the current is this. I know the length vector should be 20 centimeters, negative j hat. The B external, so let me just get this down here. This is going to be negative L in the j hat crossed with B external in the k hat. And notice J goes to K goes to I, and you get negative I hat from the cross product. Notice how important it is to be careful whether you talk about I, the current, or I hat, the unit vector. So you better make sure you're doing a good job on that. All right, so in this case, I think we're going to get, when I plug this in, I get a BLV over R times a BL. So I'm going to get a B squared, L squared, V over R. Double check. Wait, is that R squared or R? I think it's just one R. So the current here has a BLV over R, then another L, then another B, and some I hat direction crap. All right, does that make any sense? So again, let's play this back. The idea is there's no battery in the circuit. I'm going to pull this rod to the right. When I pull the rod to the right, I induce a current. The emotional, or the voltage associated with the moving rod, is given by this equation where this was B perpendicular to the rod. That voltage causes the current. Well, now there's a current in the presence of an external field, which feels a force. That force is given by ILB. And there's some sine 90 maybe and some other problems, but okay, thank you. Okay, I'm still working, okay? Yes, thank you. Okay.
There's a part I'd like to see.
What's that?
So, for the direction of the current from the rod moving, Originally, there's dots coming out of the page, right?
That's right.
So when you moved the rod, it created X's into the page?
Exactly. So it opposes the change in flux. Moving the rod to the right increases flux out of the page. This is the current loop. So notice, be careful here. When this rod moves to the right, these two sides are not connected. So this happens to be the loop. Got it? And this is a point of confusion in these problems. So when this rod moves to the right, this is the loop. The loop gets larger. There's more flux out of the page.
So
that
the
means
area,
the loop. Oh, go ahead.
The area increases.
The area increases.
So that's the reason why, because then it's more will go through that
Because
area.
yes, so flux,
Okay.
remember, flux is B times area times cosine of the angle between. Where now, okay, technically it's the integral of B dot dA. Either one of those will work. This is if you have a uniform field, we could just use this top one. The angle between is 0, right? Because the area vector is out of the page, and so is the external magnetic field. Tom, is that good for your question?
Yeah, thank you.
Yeah. And so the idea is flux increases out of the page. This X is not opposing the field. It's opposing the change in flux, which happens to also oppose the field. But think of it as opposing the change in flux. All right, more on that in just a second. Okay, so now let me read. Okay, so here's the idea. We pull this rod to the right. We get this current. We get a force to the left. There's a pulling force to the right. We're told this thing moves with constant speed. What's the acceleration?
0.
So what must be true about these two force magnitudes?
They're the same.
Equal and opposite.
Yes.
You owe me a soda, Ryan. I got
Oh.
the jinx on you there.
Oh, man.
Bet.
That's advanced. Okay. All right. And so that's cool. Now let me ask you something. Would this problem be different if instead of putting the resistor here, I put the resistor over on this side of the rails? So let me just, okay. So take a second. You've got these solutions in there. I didn't plug in all the numbers, but I think you could go through and plug in the numbers if you needed to and get some numbers. Big deal. Are the concepts clear on this before I erase the bottom half of this board? Jeez, this class is going off the rails if we keep pulling that to the right. Oh my gosh, that's so brutal. Okay, let's say I do the same problem, same rod, same external field, but I put the resistor over here. Okay, I still have B. So that's still my B external. I'm still going to pull this rod to the right with a force, capital P. And as a result, it's still going to move to the right. And it's going to move with constant speed V. My question is, does the current flip direction? Do the forces flip direction? What stuff is going to flip when I do this? Take a second to think about it. My kids brought me this steamed fish.
Oh, that's steamed fish. Honestly, when I first looked at it, I thought somehow that was like ice cream of sorts, like right when you just showed the bowl. And I was like, dang, like just pounded some ice cream. I was like, I dig it. But then you said steamed fish, and I was like, wow, I feel awful.
Green onions and ice cream would be awesome.
Yeah, that'd be good.
It'd be very Korean of me. All right. Let's think here. Let's somehow get through this damn problem and quit. If you're pulling this rod to the right, what happens to the induced current? Is it going to go the same way or the opposite way?
Opposite.
What do you mean? Explain. What do you mean by opposite?
I mean, it's going to be, last time it was clockwise, so it'll be counterclockwise this time.
Okay. So counterclockwise. Like this. Which way does it run through the rod?
Oh, same direction through the rod.
Whoa! Isn't this fun? So wait a minute. Which way is the force on it? The magnetic force.
To the left.
The same way as before. What? Oh, I can't take it. I give up. I quit. Oh. Isn't this fun? You take the same situation. We see that the induced current actually is flowing a different direction in the loop, but the same way through the rod. And it's this, is this going to be a magnetic braking problem or a magnetic make you go faster problem? Magnetic braking. And so you're going to see this a lot. You drop a magnet through a tube, you get a magnetic force up. You swing a pendulum through a magnet, you get a magnetic braking force. It slows you down. You take a rod on rails, you try and pull it this way or that way. There's a magnetic force that generally opposes the motion. Now we got to be careful here. It doesn't always oppose the motion, but it at least has a component that tries to oppose the motion. We should be very careful here. What would be different? Well, let me ask you here. So in this scenario, there's basically a bunch of magnets here like this. And the company that made this device that I tried to show in the video put a bunch of magnets underneath the rails and super glued them in place. So let me ask you here, if this is out of the page, are those magnets a North Pole or a South Pole if the field is out of the page here? Is it North Pole on top or South Pole?
North on top.
North. So this is a bunch of North Poles here. Okay. What if we redid this experiment like this? What if I put the rod here, and instead of doing this, let's say this was the magnet, and let's say I made this the North Pole and this the South Pole, and I put it like this. So again, this is the North. This is, let me get these markers out of here. So the idea here is this is the North Pole. Oh, geez, come on. This is the North Pole, and this is the South Pole. What do you think would happen then? If this was the North Pole, this was the South.
I think it would be not very strong, right? Because the dot between the field and the area would be smaller.
Nice. So take a look. This would cause magnetic fields that go out like this, right? There wouldn't be that much flux through the page. And so this problem, there would be negligible. So the same size magnets could cause no effect if they were pointed this way. What if, let me try this. Let me try another what if, okay? Let's try this way. What if I did this and I flipped all the magnets so that I flipped the north-south? So let's try this way. Let's say I put a bunch of South Poles here. And I put the rod this way. And there's a resistance here. And I let it fall down. Whoops. Let's say I do this. If I have South Poles, and I drop the rod and I let go of it, obviously there's going to be a force mg pulling it downwards. We expect, well, let's walk through the logic. If this is a South Pole, what direction is the current in the loop? Clockwise or counterclockwise? In the loop, is it clockwise or counterclockwise as this falls? I got to think. Help me out. Is South Pole a dot or an X?
Right? Because the north would be going downward.
Well, just tell me, is this, yeah, so this is a South Pole. So is this going to be representative of a dot or an X for the external?
X.
X. So South Poles, the field goes into a South Pole. So these would be X's. Then Travis, what did you say? Was that Travis?
I mean, I thought it would go clockwise, right? Like
so let me
stuck
see.
your thumb in and it would
if
roll.
you go down here, we'd run out of X's, so we'd need more X's. So it would go clockwise. Yes, I agree. Is that your thought process? So if it goes down here, I have fewer X's. I need to create an X, right? And so that means the current right here would be flowing this way, because this way creates a field into the page. If this is the current direction, my thumb points into the page and replaces some of my lost flux. So that means this one.
Oh, I see, because you're losing. That makes sense. You're losing that.
Yes.
Okay.
So
Yeah.
in this case, I'm replacing the lost flux. I'm not opposing the field. I'm opposing the change in flux. I lost X's. I need to add those back. So now, if I have I flowing this way, B into the page, notice I get a magnetic braking force, not a magnetic go faster force. All right, we're going to pick up here next time. Whew. Yeah, whatever. Watch those videos. If you can get caught up, well, you guys have talks tomorrow. But yeah, so make sure you're ready to go for your talks. And then if you can get up to this point by Wednesday. So it's a bunch of conceptual stuff. Watch a bunch of videos. It's not that crazy. So try and get done with all the problems up to 30.11 by the start of class Wednesday would be ideal. And again, it's mainly watch videos, kind of say, oh, that's neat. Oh, this makes sense. Okay. It's just conceptual. And that will help us kick ass on this on Wednesday.